Hi everyone, in this video we're going to take a look at vertical expansions and compressions. You should be familiar with these because we did them last year with parabolas. So they will be in the form of y is equal to a f of x. And if you note, should I divide both sides by a, then you will get y over a equals f of x, which you can then write as 1 over a y equals f of x. Okay, so you will see it in this format and in this format. Okay, so when we have a vertical change on a function, okay, it means that the y value will change and the x value will stay the same. Okay, so if in this case, if we have a vertical expansion or a vertical compression, it will result in a change in y. And so x will remain the same. Okay, so last year we did a lot of work with parabolas, and these kinds of transformations we did on a parabola, but in this example I'm going to use a absolute value graph, which you should be familiar with. Okay, so for the first part of this lesson, we're just going to take a look at the basic function, right? This is your basic function. Okay, y equals the absolute value of x. Now, because x is going to stay the same, I have arranged each table so that we have the same x values in each table. And what we're going to do is see how y changes. So on our parent function then, if I substitute in -2 for x, and as you know, the absolute value of a negative number is the positive number. So the absolute value of -2 is 2, and so y equals 2. And if I plug in -1 for x, I will get 1. And if I plug in 0, I will get 0. And just recall that if you are looking for the absolute value of a positive number, it will always be positive. So if I'm looking for the absolute value of 1, I will get 1. And if I'm looking for the absolute value of positive 2, I will get positive 2. Okay, so when we graph this, it will look like this. We'll have a point at 0, 0, 1, 1, 2, 2, -1 and 1, and -2 and 2. All right, and here is our graph. Okay, so what happens if we expand or compress our graph? Okay, so let's say on the next one then we're going to take a look at y equals 2 times the absolute value of x. And remember that we can also divide both sides by 2, and we will get 1/2 of y equals the absolute value of x. Okay, they mean the same thing. It's easier to work with y equals 2 times the absolute value of x than it is to work with 1/2 y equals the absolute value of x, because in number 2 your y coordinate is already isolated, so if we're going to look for other points, it's easier to use that equation. Okay, all right, so I'm going to use the same x values, right? Because if we have a vertical change, x stays the same and y changes. So let's see what happens when we put a 2 in front of our absolute value of x. Okay, so I'm going to plug in our first coordinate for x, which is on our table, -2. So we're going to go y equals 2 times the absolute value of -2, which gives you 2 times, and the absolute value of -2 is 2, so 2 times 2, which is 4, and so we get 4 for our y coordinate. And if I plug in -1, then I'm going to get 2 times the absolute value of -1, so 2 times 1 is 2. If I plug in 0, I will get 0. And just remember, if you plug in a positive value for x. The absolute value of any positive number is positive, so if I put in 1, I'll get 2 times 1, which is 2. And if I plug in 2, I will get 2 times 2, which is 4. Okay, so let's take a look at our third example then. This time I'm going to put a half in front of x, and remember, if I divide both sides by a half, okay, then I will get, well, a half divided by a half is 1, and then I will get 1y over a half, which will give me 2y equals, and in this case, the absolute value of x, okay? So the function that you're familiar with is y equals a half absolute value of x, and the new way to write it is 2y equals the absolute value of x. All right, so we're going to plug the same points in. We're going to work with the equation on the left. I'm going to start by plugging in -2, so I'm going to go y equals 1/2 times the absolute value of -2. That gives me 1/2 times 2, which is equal to 1. And if I plug in -1/2 instead of -2, then I will get 1/2 times 1, which will give me a half. If I plug in 0, I will get 0. If I plug in positive 1, I will get 0.5, and if I plug in 2, I will get 1. Okay, so let's graph these functions to see how they compare to our first one. So for our second example, -2 and +4, -1 and +2, 0, 0, 1 and 2, and 2 and 4, and we get this graph. Okay, so this is y equals 2 times the absolute value of x. And our second one, -2 and 1, -1 and 0.5, 0, 0, 1 and 0.5, and 2 and 1, and we get this graph. Okay, so if we compare the second graph to the first one, we can see that it is taller and narrower. And if we compare the third graph to the first graph, you can see that it is shorter and wider. Now, we can also compare the coordinates, okay, for y. So I'm just going to take a look at the first point, all right? So if you take a look at our first function, we have a coordinate of -2 and 2. And if you take a look at the next one, we have -2 and 4, and then the third one, -2 and 1. And if we compare our y coordinate for number 2 with the first one, and our y coordinate for number 3 with the first one, we'll note that on the second one, 4 is twice as big as 2, and 1 is half as big as 2. And if we compare those values to our a value, okay, so on example number 2 here, our a value is 2, then you can see that if I go 2 times 2, I will get 4. And if you take a look at our a value on number 3, we have a half. And so if I go 2 times a half, I get 1. Okay, so the second graph is a vertical expansion by a factor of 2. And I'm just going to call it VE2, vertical expansion by a factor of 2. And this third one is a vertical compression by a factor of a half. Okay, so let's summarize this information underneath the graphs. Notice that y changes and x is fixed for vertical expansions and vertical compressions. So what happens to the graph when y is replaced with 1/2 y? Okay, well, for example number 2 then, the equation is 1/2 y is equal to the absolute value of x. So what we're asking ourselves is what happens when I put a half in front of y. Okay, and so what happens is we get a vertical expansion. So the graph is vertically expanded by a factor of 2. Okay. So let's take a look at the point. We're going to transform the highlighted points that we have on the graph. So for our parent function, our original point is -2 and 2. If I apply a vertical expansion of 2 to that point, that means that my y-coordinate becomes twice as big, right? So I apply the 2 to the y-coordinate of 2, and my new coordinate is -2 and +4, which you can see is true on the table of values just above, okay? So for our third graph then, the equation is 2y equals the absolute value of x. So what happens to the graph when y is replaced with 2y? Well, then we get a vertical compression. So the graph is vertically compressed by a factor of 1/2. Okay, so let's see what happens when we take the point from our original function, which is -2 and 2, and we apply a vertical compression of 1/2. Okay, so that vertical compression applies only to the y-coordinate, so we keep x the same, and I'm going to go 2 times 1/2, which is 1, which agrees with the point on our table of values at the top. Okay. All right, so that's a couple of examples to show you what happens when a is 2 and when a is 1/2. Okay. Now, just on the side then, if you have your function written as we do up here, where it says 1/ay equals f of x, and if I look at example number 2, I'm telling you that a is equal to 2, okay? So if I plug that 2 into 1/a, okay? So why don't I just write that here? I'm going to go 1/ay equals f, in this case it's absolute value of x, right? So if I plug a 2 in for a, then I get 1/2y equals absolute value of x. Okay, so when it's in this form where a is applied to the y, so you have 1/a is applied to the y, then your a is in the denominator, and that tells you whether you're going to have a vertical expansion or a vertical compression. So if you have 1/2 y, then a equals 2. That means that you have a vertical expansion by a factor of 2. Okay. Now over on this side, if I write the same equation, 1/ay equals absolute value of x, and we know that the value for a is 1/2, okay, because we can see that when we have it written in the form of y equals 1/2 absolute value of x. So if a equals 1/2, then when I plug it into this version of the formula, I'm going to have 1/1/2, right? Y equals the absolute value of x. Well, how many times does 1/2 go into 1? It goes in there 2 times. Okay, and that's going to give you 2y equals the absolute value of x. Okay, so just remember that on the left-hand side, it is written as 1/a, and you have to have 1 in the numerator, and then whatever number is in the denominator tells you whether you're going to have a vertical expansion or vertical compression. Okay, so in this case, the number which is in the denominator is 1/2, and so that means we have a vertical compression of 1/2. Okay, but notice when I go 1 divided by 1/2, that gives me a 2, and that's why I have 2y over on the left-hand side. Okay, all right, so we're just going to do a little bit of a summary at the bottom here to finish off this video. Okay, so a stretch changes the shape of a graph but not its orientation. A vertical stretch makes a function shorter, which is a compression, or taller, which is an expansion, because the stretch multiplies or divides each y-coordinate by a constant factor while leaving the x-coordinate unchanged. So, vertical stretch by a factor of an absolute value of a. Now, when we write absolute value of A, it means the positive value of A, right? Okay, and so this is what we know. We know that that there are two ways we can write it. We can write it as y is equal to a f of x, so our a is on the right-hand side of the equation, or 1 over a y equals f of x. They both mean the same thing. The mapping for that, okay, the mapping notation, that's what this is that the point xy maps to x and a times y. Okay, in other words, we multiply y by some factor of a. Okay. All right. If our a value is between 0 and 1, then we have a vertical compression. The graph becomes shorter and wider. Okay. If we have the a value being greater than 1, then we have a vertical expansion. Okay, so let's just quickly review what that looks like in terms of the equations that we have up above. So our second equation was y equals 2 times the absolute value of x, and of course we could write that as 1 over 2y equals the absolute value of x. In this case, a equals 2. Then in the second, or the third equation, sorry, up above, we had y equals 1/2 absolute value of x, and of course we could write that as 2y equals the absolute value of x, and so we get that a equals 1/2. So when a is 2, we have a vertical expansion, okay, where the absolute value of a is greater than 1. A vertical expansion of 2 where the absolute value of a is greater than 1. And then on our third example, we get a equals 1/2, which means we have a vertical compression of 1/2. This is where a is between 0 and 1, and then we have a compression. Now, vertical compressions and expansions are called vertical stretches, and we say that it is a vertical stretch about the x-axis. Okay, so a vertical stretch about the x-axis. Okay, that's the terminology that you will see in your homework. Okay, for vertical stretches, the invariant point is at x and 0, meaning on the x-axis. Okay, all right, so that will conclude our video for vertical expansions and compressions.